Welcome back, everyone, to a special episode of Physics with Mr. McQueary. Today is all about manipulating the universal gravitation equation when we change things like mass or the distance between those two objects. So, for example, some of them are straightforward like this one. When a mass is tripled, what happens to the force of gravity? Okay, so we have our helpful equations in front of us, and we're going to go ahead and get rid of that g, all right? The reason why we're getting rid of that is because G was present with the original setup and the new one now that one of the masses is tripled. So imagine we started out with something maybe like this over here, and there's a distance between them. Okay, and now we've tripled one of those masses. Same distance. All right, and the mass of object 2 hasn't changed. It's just object number 1 that changed. Okay, so the only thing that's changed here is M1. So everything else will stay the same. Fg. Okay, we're not going to worry about G here. R has stayed the same. M2 has stayed the same. M1, though, has tripled. So we're going to replace that with a 3. So overall, the force of gravity between those objects has tripled as well. So that's where that 3 comes in. We can also change both masses. So maybe now in our picture, all right, those masses got a lot bigger. All right, the distance between them, I know it's not a good job on this picture. We're going to say the distance hasn't changed. So just pretend like those are the same right there. But the masses have changed a lot. So once again, get rid of that G because it's the same in both of those. Fg is equal to, well, we said the distance doesn't change. And we got mass 1 has been quadrupled, mass 2 has been quadrupled, and those are multiplied. So now the force of gravity is 16 times stronger than it used to be. All right, so kind of the same thing we did before, instead of substituting in for one mass, now we have 2 because 2 things have changed. In the third example here, we're going to finally get into distances. So now we have the same objects that are pretty far apart, and now we've just kind of cut down on the distance between them. And you notice here that I'm using D for distance and R interchangeably here. So if that's confusing, I apologize, and I will write R for this example here. All right. So you can see that it's changed quite a bit. All right, but the masses are still the same. So get rid of that G. If G equals, all right, mass 1 has not changed, mass 2 has not changed. So we're going to leave them alone. And the distance between them has changed by 1/2. And there's a square here, so be careful on that. Okay. 1/2 squared is the same thing as 1/4. And for my math people here, you'll notice that when we have a fraction in the denominator here, dividing by a 4th is the same thing as multiplying times 4. All right, a little math extra right there for you. So the object has been quadrupled in the amount of force that it's experiencing. All right, easy to miss that one. Last but not least over here, we're going to give you a combination when your masses are changing and your distance between them are changing. So we have 2 objects over here with a distance between them, and a couple things happen. Number 1, the distances increased quite a bit. It's doubled. So now our distance is a little larger, and one of the masses is tripled compared to what it used to be. So we'll be changing multiple things again in this. If G is going to equal, well, mass 1, we didn't bother to change. Mass 2 did change. It's been tripled now. And the radius has been doubled. Okay, so if we simplify this, we get 3 over 4. So it is 3/4 of the original strength. Okay, those are a couple examples there when your masses change and when your distances change. A quick and easy way to go about it is to just go about it with fractions like this. So hopefully this helps you when you're solving your relationship problems with universal gravitation. Till next time, see ya.